It is warm in here. All right, so here's the deal. R and R squared. So easy to confuse them, and you feel like they do about the same thing. And in some ways, I guess you could say they do, but they are different, but I also understand how confusing it can be. So years ago, I probably mentioned this before, I used to teach just a regular stat course at LCM. Okay, it wasn't AP back then, but my counterpart at Long Cruz High School, she had a master's in statistics. So I actually still have an email that I had written to her that I saved, and my email was, okay, what is the difference of R and R squared? And I have this long email from her trying to describe the difference. It's difficult to understand because it's really kind of subtle. So for the first couple years I taught AP, I kind of just blew over it a little bit. It's like, just when they ask you about R squared, say this. If they ask about R, say this. I feel like I'm doing a disservice. So I did some research over my first couple years, and I finally found some diagrams that kind of at least helped me understand a little bit better. So that's what I'm going to do with you is I'm going to show you these same diagrams and show you where the stuff comes from the diagram. That's why I said it's not going to be an exciting day of notes, and I know that, okay? So there's also an issue with the notes. If you remember, there was one other place that I said the graphics did not copy properly, so there's a big chunk of stuff that's missing from the notes. We'll get there. All right, so what I'm going to do, so we did residuals yesterday, so I'm picking up on page 11 of the packet, and I have this basic little data set here. So bivariate data, this would be an n size of 5 because there are 5 ordered pairs, and I have it in both of my calculators. Now, what I tried to do last hour was I tried to do this page on both calculators, and then I went to the next page, and I tried to do it on both calculators. I'm going to do the first page just on one calculator, and then I'll do the second page on the other one. Now, you can still be on your calculator doing both pages if you want, because there's actually going to be something I'm going to show you, and I'll do the 84 on this one because I actually want to show you something on the 84 that you have to tell it to do that the Inspire just does automatically, okay? All right, so I had this data entered in my 84, and so that's in my L1 and L2. And when I entered it in my Inspire, by the way, I literally just called it X and Y. So, and again, you guys can all do this if you want, but I'm going to create a new column of Y hat. Now, Y hat goes with your regression line. It is your predicted Y values. Okay, so I'm going to need to make that column. I need to actually do my linear regression. All right, so I'll come back to that. Let's see. Use your calculator to find R. Okay, to get R, you're going to have to do linear regression. But I also said, let's get X bar, standard deviation for X, and etc. So what I'm going to do for part A, and again, I'm working on this one on my 84, but Inspires, you could do it yourself also. So I'm going to do calculations, and I'm going to do 2 variable statistics. And Inspires, you can do this also. If you do 2 variable statistics, basically what it's doing is it's not treating it as bivariate data. It's just saying, okay, so you have 2 columns of data. Okay, for all they know, it's 2 totally unrelated things. So L1 and L2, I calculate. So I have an X bar of 3. I have a standard deviation for X of, I'll call it 1.58. And if I arrow down a little bit farther, I have a Y bar of 5.4. And I have a standard deviation for Y of 3.21 approximately. Okay, so when you do 1 variable statistics, it's literally just doing 1 column. If you do 2 variable statistics, it's doing both columns, but it's not treating it as bivariate data. It's just literally treating it as separate. Like the first thing could be how many cars are in the parking lot. The second column could be how many shoes you have in your closet. Okay, they're totally unrelated. If I want R, or the regression line, that requires a calculation of linear regression. And both calculators have 2 linear regressions. They do the same thing. One of them is going to look more like MX plus B. In fact, as I think on the Inspire, they call it MX plus B. And then they each have this other one that matches our formula page, A plus BX. They do the exact same thing, but I'm going to choose number 8 because that is truly what matches our formula page. So L1, L2. All right, here's the part that I want to show the 84s. Store the regression equation. So we could write the regression equation after we get the values for A and B. But if you choose store, you can store the equation automatically in your calculator. Now, the reason I'm doing this on the 84s is Inspire's, yours do this by default. It automatically stores it, okay? So I'm going to tell it to store. Now, 84s, if you want to do this, you press variables, VAR. You know equations have to have a y equals, so we have to choose y. We're going to get the equation of a regression line, which is in fact a function. And then you can choose whichever y variable you want to use. I just always use y1. And then when I tell it to calculate, which by the way, I forgot to turn my diagnostics on, so I'm not going to get my R value anyways, but I now know that A, which is my y-intercept, is negative 0.3. I know my slope is 1.9. So my regression equation is going to be y hat equals negative 0.3 plus 1.9x. Now, you know sometimes when you do that, you get those really long decimals. Well, the issue is if you store it, when I press Y1 and go, it's automatically in there. So if there are some really long unrounded numbers, the calculator just puts them all in there for you. And again, the Inspires do that automatically. It stores it in F1 automatically, okay? I won't actually do it, but if I did, if I started on my Inspire, I could do statistics, I could do calculations, and I could do option 4, linear regression. It's right there. It's telling me that it's going to save the regression equation to F1. So it's automatically going into its memory for you, okay? So you don't have to retype the equation, is the cool thing. You don't have to retype the whole thing, all right? Now, by the way, I said I forgot to turn my diagnostics on, but if you did, what do I have for an R value here? Was it 0.9 something? 0.936. 0.936? Okay. All right. So I stored my regression equation. All right, now, because I now have y hat stored in there, I am now finally ready. I can make this column. So that's going to be my L3. And if I were doing this on my Inspire, I would probably call this PY, and I call that for predicted Y value. That's just what I do. It's my routine. So I'll do this, however, on my 84. I'm going to stat, and I'm going to go to edit, and I'm going to make a new column. So go up to your formula bar, regardless of what kind of calculator you have. Inspires, you have to press equal. 84s, you don't. So what you're going to do now is you say, well, I want this to be my y hat values. You have an equation stored that will calculate your y hat. So 84s, if you press variable, go back to your y variables, choose function, choose y1 if that's where you stored it, and you literally write this like function notation now. So you open up a parenthesis and you say, I want you to take the equation that I have in y1, and I want you to use every number that I have in L1, and I want you to put it in that column. Boom, it just did it. It just took the 1 and plugged it in the equation and got the answer. It took the 2, plugged it in, and got the answer, and the 3. And it did it all for you that fast, okay? Inspires. All right, I said I wasn't going to do this, but maybe I should because I want you guys to see how this works in case you ever want to do this yourself. Right here. Okay, so Inspires. You could now say, and I'm going to do my regression now. So I will do the full regression. I actually will do it. So I have a column called X. I have a column called Y. It is storing my regression equation in F1. Okay, so there's my regression. There's my A, there's my B, there's my R squared, there's my R, and it's stored F1 for me. Now you guys, The next time you go to press your variable button, you're going to have a really long list now because it just did a whole bunch of calculations for you, okay? So if I now want to make that new column, I'm going to call it PY for predicted Y, PY. I press equal, and I press variable, and look at what the top one is, F1, because the calculator knows that it just put something in F1 for you. So I'm going to choose that. The Inspire even puts the parentheses there for you. And you say, I want you to take the function that's in F1, and I want you to plug in everything that I have in my X column. And it just did it, without having to retype the whole equation. Now, this equation was kind of short because I made sure that the numbers didn't have a lot of round off, okay? They were very precise. But you don't have to retype these if you don't want to. Was there a hand up or are people just stretching? What's up?
Oh, I put it in my calculator.
It wouldn't work? That's a user error.
Well, no, I go to L3, right?
Yep.
And then I go.
Are you in the very tippy top?
Yeah.
Okay.
And then I hit variable, and I hit function. Right?
If you're in the tippy top,
Yeah.
and you are, so I'm going to clear mine and pretend I didn't do that. Okay, so I would hit variable, Y variable, function. I chose 1, and then in parentheses, L1.
I didn't do that.
Yeah, it doesn't know what to do then,
Okay.
because you're telling it to try to multiply a function times a variable, and it would be very confused. Okay, that's what it's got to literally be function notation. You got to literally make it like function notation. Okay. All right. So we now have a column. Actually, I cleared mine out. I need to fix this now. Variable function of L1. Okay, those are my predicted values. So this is the part that I said, okay, we could write those down, but I'm not even going to bother. And what I'm going to do now is make a new column of Y minus Y hat. That is your definition of a residual. So I'm going to make an L4. Inspires, if you are following along, call it R or RES. Call it something to remind you you're doing residuals. All right, so in this one, I'm going to do residuals are always the real Y value minus the predicted. So the real Y value is 2, column 2. Minus the predicted was L3. Got it. All right, those are my residuals. Now, every time there's a negative residual, it means you have a dot that would be underneath the trend line. Every time you have a positive residual, it means you would have a dot that is above the trend line. Now, let's see. We could probably do this math without, I think we can do this in our head. Let's add up. Look at the 2 positive residuals. What do the 2 positive residuals add up to? 2.2. Got it. What do the negative residuals add up to? For a total of? 0. All right. Do you remember when we did standard deviation, we had the one column that always added up to 0, and I said that's why we square it. We got to get rid of the negatives so they can't all cancel each other out. You got the same thing going here. Okay, so that's why the next column is we say, okay, this column is not going to help me. So I'm going to make one more column. I'm going to take L4 and I'm going to square them all because that'll get rid of the negatives. Cool. Got rid of the negatives. What we need though is the sum of that column. So now I could sit and just add those up if I wanted to, but what I just do is I go to stat, calculate one variable statistics, and I want to use L5 because that's where I'm at now. I'm at L5 right here. All right, so I'm going to take L5 and I'm just going to say, what do I get? Sigma X is 5.1. Reminder, Sigma X. I didn't use my X column. I know what I told it to do. I told it to use column 5. So Sigma X is this Sigma. So this is 5.1. Now you might get that number and say, awesome, 5.1. What you did, here's the graph of the ordered pairs. Okay, we said some of them had negative residuals, some of them had positive residuals, If you add up these three negatives and these two positives, they will always just cancel each other out and give you 0. For every positive, there has to be something negative to counteract it. When you squared that column, you actually were doing what our French friend did, Adrian Legendre. You were actually doing the math behind the least squares regression. You squared this distance, you squared this distance, and you squared this distance, and this one, and this one. You squared them all, and when you add up all of those squares, all of those areas, they all add up to? Nope. 5.1. They add up to 5.1. And that 5.1 is the smallest sum that you could possibly make. And that's where the least squares regression line comes from. You're trying to minimize those squares. So you got to think about all that math is going on behind the scenes in the calculator, and it's figuring out how big these squares could be, and it's coming up with the smallest ones possible, okay? Statisticians call that total SSE, the sum of the squares of the errors of prediction. Okay, a residual is an error in prediction. For this point right here, the line is an over prediction from the real thing. For this one, the line is an under prediction for the real thing. Every residual is kind of like an error from the trend line. So you found the sum of the squares of the errors. Okay, so before we move off of this, we calculate average error. Now, your book uses lowercase s. Minitab will use a capital S. Okay, so whether it's S or capital S, they're used interchangeably, very confusing, but whatever. But what we did when we got that 5.1, we did this math right here. We took the residuals, we squared them, we added up. We got 5.1. If you divide by the n size minus 2, and remember our n size was 5 because there were 5 ordered pairs, so we're going to divide by 3, and we're going to take the square root of that whole answer. And if you feel like you're doing standard deviation, you kind of sort of are. You are calculating the average error when you make a prediction. The y-hats are used to predict. The residuals give us the error. And when we do this, it gives us the average error. So if I take the square root of 5.1 divided by 3, I get 1.304. That is considered the average error. And this is how you have to be ready to interpret this for AP. There's a lot of these in this chapter. We interpreted S, we interpreted the y-intercept, we interpreted R, we're interpreting S, we're going to interpret R squared. There's a bunch of these, okay? When using the least squares regression line to make predictions, the average error in predicting Y is about 1.304 for the example we just did. So every time you use the trend line to make a prediction, you will be off by about 1.3 on average. Okay, your phrasing is almost exactly like standard deviation, almost exactly. Okay, so for part 2, I'll switch and I'll do this on my Inspire now, just to be different. Okay. All right, and I'm actually going to literally start over. So I'm going to make an X column, which was 1, 2, 3, 4, 5, and I'm going to make a Y column, which was 1, 4, 5, 9, 8. 1, 4, 5, 9, 8. Okay, got my date in my Inspire. All right, going to be really similar to the same math. And 84s, if you just want to override your old L3s and L4, you can just do that. We don't need those anymore. Okay. What we're going to do now is we're going to do another type of kind of like an error. Okay, but instead of doing Y minus Y hat, we're going to do Y minus Y bar. Now, why do we use Y bar? what you might not remember, and y bar was 5.4. This was way back in chapter 1, but one of the ways you can interpret a mean is you could say, if all the y values had been the same, they would have been 5.4. Wouldn't that be true? If all of these were 5.4, wouldn't the mean be 5.4? Okay, so what this is doing is saying, okay, we know that the y values were all different, but let's say they were all typical. They were all 5.4. Then we could say that this one was below typical, below typical, below typical, but above and above. And this column, what I'm going to find out is how much above or below. So I'm going to come up here and I'm just going to call this one, I'll just call this S for subtract. I'm just making it up, whatever. Actually, I'm going to change it to SUB for subtract. I don't want you to confuse it with S that we just talked about, that formula. Okay, so I'm going to set up a formula, and I'm going to say I want to take all the y values that I have, and I want to subtract 5.4. Okay, so I just got through saying which ones were below, below, or above. Okay, below, 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 above, above. Add up the aboves. How much above do we have? 6.2. Add up the belows. How much below do we have? Yeah, probably not a big mystery. That column is going to come out to be 0 because that's how a mean is calculated. For every bit that's above the mean, there has to be something to balance it below the mean. So we square it so that we can actually do some math on it. All right, so I'm going to call this SUB for subtraction, but then I'm going to call it SQ for subtraction squared. So equals, I want you to take the subtraction column and I want you to square everything. Cool. Now there's no negatives left. And now I can figure out how much do those add up to. And I could just sit and add those up, or I'll just do one variable statistics, but I'll do it off of the column that I called sub-square. And again, the calculator is going to call it X, but I know what it really is. Sigma X, 41.2. And statisticians call that SST. And that stands for sum of squares of total variation, because that was already the variation that we would have expected just in the Y column alone. Forget about the bivariate data from the trend line. The Y column alone, I would have expected everything to be about 5.4. So visually, what you did here, this line is the mean line. That's your Y bar equals 5.4. When we did the subtraction column, you were calculating these distances. One of them was 4.4 below. One of them was 1.4 below. One of them was 0.4 below. And then there were the two that were above, and they were far enough above that they balanced out all the other belows. So that was the column when we subtracted, but then we made a column of squares. So all of these squares and this square, all of these squares, if you calculate the area of all these squares, they all add up to 41.2. So that's the error we would have expected in Y alone. The other one was the error we would have expected when we predict Y. And then I take the two diagrams and I superimpose them on each other. 5 dots, trend line, mean line. Now, I'm not going to draw the squares on top of each other, but what I am going to point out is, I'll just use this one as an example. We started by calculating those vertical distances and those squares. And that's what statisticians call SSE. So this is called SSE, the distance from the point to the trend line. Those give us all the SSEs. If we take that point and go all the way down to the mean line, that's what gave us our SSTs. And there's a third thing called SSR. Can you guess where it is? It's that little missing component right there. That is called SSR. And that stands for the sum of the squares of regression. And this is the diagram that I said. You look at it like, I still don't know what that means. I get it. It's very difficult to understand. But what it comes down to is SST is what they call total deviation. That's what we would have expected on Y if Y was just its own column. We would have expected all of this potential variation. And then we have the SSE, and they call that unexplained deviation. Because the SSE, remember, you're using the trend line to make a prediction. And so we think our prediction should be good. And when they're not good, we're like, why? Why didn't it work? We call that unexplained. Well, if this one's total and this one's unexplained, the other component is called the explained. We're like, okay, we know what the total was. We don't know why this part happened. But then it's like, okay, but now I can figure out why this happened, because if this was my total and this was my unexplained, well, okay, then that makes up the difference. Bottom line is your SSE added to your SSR will always equal your SST. Our SSE was 5.1. Our SST was 41.2. So can you do the math and tell me what SSR is? 36.1. That's the part that you're going to use to calculate R squared. SSR is explained. Your R squared is going to calculate what proportion of your variation is explained by the trend line.
Why is the one that you have to use the other calculation to find the explained calculation?
Because when you make the trend line is I'm using it to predict what I think Y should be. And when it doesn't work, we just say, well, why? So we call that unexplained. But then by default, we're like, okay, if I have a total, once you know how big the unexplained is, then you're like, okay, it means the rest of it must be this much. It's like if someone tells you, well, the total cost is $12 and this item is $5, then you know the other one must have been $7 by default almost. It's like, okay, not that I really have an explanation for it, but if that much is unexplained, I certainly have a way to now calculate the other one, okay? So what you're going to do to calculate R squared is you take what's called the explained variation, which in this case was 36.1, and you make it a proportion out of the total. And if you do 36.1 divided by 41.2, you get 0.876. Which, by the way, because it is a proportion, we often write that as a percentage. We would say that 87.6% of the variation can be explained. 87.6 is explainable based on the fact that there must have been 12.4 that was unexplainable. Okay. Now let's go back. What did you tell me R was? 0.936? Let's see what we get if we take 0.936 and we square it. 0.876. Mathematically, they really are that connected. There's R and there's R squared. Okay? They're that connected. But statistically, what they represent, it's different. The R is describing the strength of the linear relationship, and the R squared is describing the proportion of variation that we can accept as explained because of the variation and the relationship between the two variables. Okay, it's very subtle, but the R describes the strength of the relationship. The R squared describes the variation when you're using the line to make predictions. Okay, it has its own name. It's called the coefficient of determination. R squared measures the percent of variation in the response variable that can be explained by the regression line. And this is your phrasing. About 87.6% of the variation in Y can be explained by the linear relationship with X. Good news. I have never, ever seen them do anything with SSE, SST, or SSR on the exam. And I know some of you are sitting there saying, then why did you just spend this whole time doing this? Because in the past, when I didn't, when I just kind of blew over R squared, that bothered my students. They saw the math here, but then they're like, but what does it mean? I'm hoping at least it will give you a little bit of a visual that you're like, okay, R squared deals with this piece divided by the total. And that's really what it comes down to. Okay, you have the piece from the point to the trend line. You have the piece from the point down to the mean line. And then you have that other little difference. And that's what you're measuring. That other little difference divided by the total.
But what if it's the same?
What if it's the same, like, if it's, what do you mean, if it's the same? I'm having a
So
problem with
like
your
you have the
pronoun.
line that goes between the point and the.
Oh, right here?
Yeah.
Okay, so that one, so all of a sudden what you would have there, for that one point, obviously that is, in the calculation, that would be a little bit unique, okay, but it's all of this is all of these together anyways. So it's taking every one of these, you have to picture on every one of these, you have to draw an SST, an SSE, and an SSR, and it's putting them all together, okay? So that's the reason I didn't choose one of those to draw the diagram. I wanted you to see the three components, okay? I know, like I said, I know this is still a little bit money for some of you, but it at least gives you a little bit of background where R squared comes from. It's not just some big random mystery, and it's also not just R squared, okay? It comes from something else. All right, so on the next page, which is the last page of the real notes, this is where the diagram is missing. This was supposed to be a full Minitab output, and the graphic didn't copy. So I'm gonna pull up, this is mine from another year. All right, so if you see a linear regression Minitab output, I think I already mentioned this, okay? How it's named, price versus catch. That's actually on here. If it's phrased like this, you should automatically know that the first word is Y, so that's your response variable. And then versus, the second word is X, and that's your explanatory variable. That is just how, and that's not just Minitab, that's really common. It's Y versus X, or Y against X, okay? So this is showing the price of Peruvian anchovies and the amount of fish that has been caught, measured in millions of metric tons. Okay, so price is my Y, and then how many fish is my X. All right, so now I'm gonna go back to this one. When you see a printout from Minitab, first of all, the stuff that I don't have boxes around, you can ignore it. Okay, you don't have to worry anything about that yet. All right. And I'll go back to the other page and help you write something down to hopefully help you remember this since your graphic is gone. In an equation, a linear equation, y equals mx plus b, your y-intercept is called a constant because what does it not have attached to it? A variable. So when you look at your printout, whatever number is written next to the word constant, that will be your y-intercept, okay? Your y-intercept, the number written next to the word constant. Okay, so when you see a Minitab printout, wherever it says constant, that number is your y-intercept. Now, when you look above it, it's going to look confusing because you're going to see COEF. You're going to be like, coefficient. Okay, yeah, whatever. Ignore it until the next row. Because it does say coefficient, this number is the coefficient that goes next to whatever variable is identified here. Price versus catch. That's how many fish have been caught. That's the slope. Whatever number is written next to the x variable is the slope. So the slope is the number written next to the explanatory variable, and it will be under the header of coefficient. To remind you, you know that slope is the coefficient on x, okay? Slope will be the number written next to the explanatory variable under the header of coefficient. So when I look at this right here, my y-intercept is 452.12. My slope is negative 29.42. So when I want to write the equation, I will be predicting price. The y-intercept is given as 452.12. The slope is given as negative 29.402. And that is written next to the word catch because we're counting how many fish we catch or how many anchovies. On the Minitab output, you just need to learn where to grab the numbers from, okay? Now, to interpret the slope, we did this yesterday. When you interpret slope, go back to algebra. Take your slope, which is negative 29.402, and put it over a 1. And always start with that 1. For every increase, because the 1 is positive, in 1, and the 1 is x. What is x measuring? How many fish I've been caught in millions of metric tons. For every increase in 1 million metric tons of fish caught, the price, because that's my y, is expected to decrease or go down, and I know that because of the negative, by about $29.40. This part is always the same. You always start by saying for every increase in 1, and then identify your x variable, okay? You always use the word expected. You always use the word about. And whether you say increase or decrease just depends on whether your slope is positive or negative, okay? Does the y-intercept have meaning? Write the ordered pair, 0, 452.12. And remember what x is measuring. That's how many fish I catch. And y is price. would it make sense to say that if I catch no fish, they'll sell for $500 or $452.12. Okay, if I don't have any fish, guess what I'm not doing? Selling any. Okay, I would say that there's no meaning then. It happens. The y-intercept doesn't always have meaning. All right, here's the new stuff. Interpret S. S is going to be a lot like standard deviation, but you're going to start with the phrase, when using the least squares regression line to make predictions, the average error when using the least squares regression line to make predictions about cost the average error in those predictions will be about, and then you come back here and you say, oh, the S value was 71.69. So every time you use that regression line, you're predicting price. Every time you could be off. You might be predicting high, you might be predicting low. This is just saying that on average, you're going to be off by about $71.69. You could be off on the high side, you could be off on the low side. It literally is just like standard deviation. It's telling you how far, instead of saying how far from the mean, this is saying how far from the real value is it, okay? Interpret the value of R squared. And again, this one, you can start the same way. About blank percent of variation in, put your Y variable, which is price, can be explained by the linear relationship with amount of fish caught in millions of metric tons. And the R squared will be given to you in the printout. 73.5. Fill it in. What they don't give you on the printout, Minitab will not give you R, because they assume if we give you R squared, guess what you can figure out? Okay, so they give us R squared is 73.5%. So let's change that into an actual decimal so we can do some math with that. So if they give you R squared, how do you find R? All right. Time warp back to algebra 2 for me. When we did square roots, what did I remind you of over and over and over again? There's actually plus or minus here. So you literally can whip out your calculator and say, what is the square root of 0.735? And it says 0.857. But it can't be positive or negative. It's got to be one or the other, and you will be expected to know. How are you going to know? It's the slope. If the trend line has a negative slope, it means the dots must be going down, and therefore your R must be, you have to be able to remember to do that. Okay? And then the last page is just a couple of reminders. Correlation and linear regression, R squared, whatever. It's all linear relationships only. Correlation makes no distinction between X and Y. You could change X and Y on your graph and you're not going to change R. But if you change your X and Y on your graph, you will change your linear regression. Okay? If you are writing the equation of the regression line, if you switch your X's and Y's, You're changing things, okay? None of this stuff is resistant, and we talked about that. All right. Chapter 3, notes are done.
Oh, yeah.